The first theorem in this section says let f be differentiable over an open interval I. That just means that our curve will have a derivative that we can figure it out. It says if f prime of x is greater than 0 for all x in I, that just means basically on this interval, if the derivative is strictly positive, if it is greater than 0, then f is increasing over I. And it also says if f prime is less than 0 for all of those values in the interval, then f is decreasing over I. So it's sort of saying on a particular interval of x, like we were kind of saying before, like looking at this past video, like if it's increasing from -5 to 3, then it says the f prime will be positive. And again, this makes sense because if I took the derivative of any point to find the tangent line here, the slope is going to be positive on this interval, again, because I can see it's going up to the right, any point along there. Now, if I took an interval that was decreasing, say for example, I let interval I be from 1 to 4, and I took any of the tangent lines on this curve, no matter where I would align my ruler with on this curve, tracing through it, it's going to be negative slope down and to the right. Decreasing means negative slope, and that's exactly what this is saying. So this is a theorem that you shouldn't need to memorize because it's common sense, and that's what we'll experiment. We'll practice using it to find things, but basically it's a way of determining whether a function is increasing and decreasing by using the derivative. So let's check out example number 3. It says let f of x be equal to a polynomial, x to the 4th, blah blah blah. Find the intervals of increasing and decreasing, and we can check by graphing, or let's do it first by finding the derivative, because like we did before, you can always figure this stuff out by looking at a graph. However, a graph isn't always perfect, and we might not be able to tell for certain what's happening within the graph. But basically, we could always start by taking a derivative. F prime of x is equal to, well, using the power rule, this would be 4x cubed plus 12x squared minus 4x minus 12. And so there we have the derivative of this particular function. And if we're wondering, well, how do we go about this from here? Basically, finding the values of 0 can help us tell whether it's increasing or decreasing. But basically, if this whole polynomial is positive, then it will be increasing. And if this whole polynomial is negative, then it will be decreasing instead. And you could plug in random numbers into this to try to figure out, okay, when is it increasing and when is it decreasing? Or you could set it up as an inequality. 4x cubed plus 12x squared minus 4x minus 12. If I want to know when it's increasing, I need to set it greater than or equal to 0 and solve when is this true. I know for some of you guys it's been a while since you've had algebra, but basically the method of solving such equations or inequalities would be, I want to set it to 0, which is true because it's increasing. I'll go ahead and write that out. This is going to be when it's increasing. And when it would be decreasing is if all of that is less than 0 instead. And so, but basically the way that I solve a polynomial equation or inequality is first has to be set to 0, which it is. Then we factor the other side, and after factoring it, we can solve the zeros by setting each factor equal to 0 by the zero factor property. So let's just do a quick recap. But factoring polynomials such as this, you may not remember, but there's a very specific technique which is called factoring by grouping. It's a process where you group them into 2 individual components, and then you factor out the greatest common factor, which is what we call the GCF, from each. So like the first 2 terms, notice that there's a common factor of 4x squared. And if we factor that out, we'd be left with x plus 3. And in the second group, there's a common factor of -4, which would also leave x plus 3 remaining. And since these 2 groups have the common factor of x plus 3, we could factor out the x plus 3 from that. And what that would leave us with is 4x squared minus 4, x plus 3, greater than 0. And if this technique is something you don't recognize, feel free to like Google it, or I have a video on it somewhere on my channel, but it's called factoring by grouping. So just search that key term and you'll find some videos on it. And actually from here, this is a common factor of 4, so I could factor that out as well. So if I pull out 4 from there, that would leave me 4 times x squared minus 1. And also, you might recognize x squared minus 1 is called the difference of squares. That can also be factored as x plus 1 times x minus 1. So in these chapters, it will call upon your ability to factor polynomials. If you're rusty on this, I would advise going back and practicing some of these, going back and looking at some of your factoring techniques. And again, I have a lot of them. I have videos on a lot of these techniques on my channel somewhere. And if you can't find them, feel free to email me and I will happily help. But basically what we end up with is 3 values here of the 3 zero values. And those will dictate whether it's increasing or decreasing and so on. And actually ways of determining whether it's increasing or decreasing, basically it will be 0 on these particular 3 points. So the method of determining the answer algebraically from here is if you take a number line and you graph those 3 points, basically our graph 1, 3, and -1, those 3 values that I just solved. Then basically in between those points, it will be increasing and decreasing based on the solutions of these equations. Because like if I'm imagining, say for example, I plug in the number 0, what I would end up getting is 1, -1, and 3. And that would be ultimately negative number because all that really matters is what the sign comes out giving me. And this is actually pretty much the process of what's called the first derivative test. But let's go ahead and kind of divert from the algebra for a second because we're going to come back to why a lot of this makes sense if I'm losing you right now. But essentially the thing of what I was saying is it should be decreasing in between those two. And if we go ahead and look at the graph for x cubed, the original graph, not the derivative, x to the 4th, because I'm trying to figure out the properties of the original function. And the derivative will help me know when it's increasing and decreasing. Again, one of the many things you can use a derivative to figure out mathematically. And if we go ahead and I'm going to go ahead and zoom standard on this. And notice that in between the intervals of -1 to 1, this is decreasing. That makes sense. And also between -3, whoops, I made a mistake here because this is 0, -3, not +3. So let me go ahead and correct that. Just a simple little error with the sign. Notice that between -3 and -1, this graph is increasing. So in this interval, increasing. And then from 1 to infinity, 1 to the right, it's increasing. This is from, don't worry about that. That's just from something else I was doing. Should not be there because that has nothing to do with this function. But basically from 1 to infinity, it's increasing yet again. And also to the left of -3, again, it's left to right, it's decreasing from over here down to -3. And essentially this polynomial has fluctuation, and those fluctuations can be determined algebraically. And this is actually what's called the first derivative test, which I'm going to work up towards. But basically the derivative and the way in which the derivative factors plays into those answers because it has to do with solving such an inequality. But at the end of the day, the intervals, again, kind of like I'm looking for my final answer, it's increasing on the intervals from -3 to -1 and from 1 to infinity. And it's decreasing on the other intervals from -infinity to -3, including -1 to 1. So let's define another term. A critical value is a point on a curve where the slope changes or where it will, but basically there's a change in the way it's switching from increasing to decreasing or increasing to constant. Like looking at the previous example, this graph where we're determining, it's decreasing, increasing, constant, increasing, decreasing. Every single point that's been filled in on this curve is what's called a critical value. And basically, because notice here, we'd say the slope is negative, it's decreasing, but here it's where it changes. It changes from negative to positive, and this is what's called a critical value. Same with here and here. because from here it's changing from increasing to constant, constant to increasing, increasing to decreasing. Every single point where it has a change in the slope is a critical value. Another way to remember this is critical values always occur at what we call the localized minimums and localized maximums. Now this is on the next slide, but basically notice some of these points correspond with, on the curve, like down here, this is the smallest value in the entire graph. There's nothing that goes lower, and that often corresponds to critical values. But the way that we denote a critical value is either by the coordinate, like for example, we could say this one is -1, comma, well, we don't know the y values because they're not shown here, but it's usually just by labeling them as x. So the critical values occur at x is equal to, well, 1, 2, 3, 4, 5, -5, x is equal to -3, x is equal to -1, x is equal to 1, x is equal to 4, and x is equal to 5. So basically we would say that this particular graph displays 6 different critical values on the graph. So again, say we were trying to figure out the critical values in the previous function. Again, step 1 would be to find the derivative f prime of x, which was 4x cubed plus 12x squared of minus 4x minus 12. And to solve when it, well, actually, let's go ahead and read the definition. But basically, the definition of, well, let's look right below. It says a critical value of a function f is any number. Well, again, we could figure out these criticals just by the critical values by looking at the graph, but it's basically the points in between where it's changing from increasing to decreasing and so forth. Like, again, kind of like with here, well, we know it changed at -3, the endpoints of that interval, or right down here, it's like the bottom of the curve critical value. Here's another critical value at -1 where it changed from increasing to decreasing. Then at 1, it changed from, again, decreasing to increasing. And then those would be our 4 critical values, which, again, you could determine, sorry, there was 3 critical values. X is equal to -3, x is equal to -1, and x is equal to 1. And those correspond with the algebra of how that was factored after all is said and done.